Greetings, fellow science enthusiasts. Today we're diving into the fascinating world of work, energy, and power. These three fundamental concepts form the bedrock of physics and help us understand how the universe operates. From the smallest atom to the largest galaxy, work, energy, and power are constantly at play. They explain why things move, how they interact, and the very essence of motion itself. So, buckle up and get ready for a thrilling ride through the fundamentals of physics. Now you might be wondering, why are these concepts so important? Well, understanding work, energy, and power allows us to analyze and predict the behavior of physical systems. It helps us design efficient machines, optimize energy consumption, and solve real-world problems. From building bridges to launching rockets, these concepts are the cornerstones of engineering and technology. So let's embark on this journey of discovery and unravel the mysteries of work, energy, and power together.
Let's start with work. What do we mean when we say work in physics? In our everyday lives, work might involve studying, cleaning, or even lifting heavy objects. But in physics, work has a very specific definition. Work is done when a force acts on an object, causing it to move a certain distance. In simpler terms, if you push a box across the floor, you are doing work on the box.
To calculate work, we use the formula work W equals force F times distance, d times cosine of theta, where theta is the angle between the force and the direction of motion. The unit of work is the joule. 1 joule is equal to the work done when a force of 1 Newton is applied over a distance of 1 meter. It's important to note that work is a scalar quantity, meaning it has magnitude but no direction.
For instance, imagine lifting a 10-kilogram weight vertically upward by 2 meters. The force you apply is equal to the weight of the object, which is approximately 98 newtons. The work done in lifting the weight would be 98 newtons times 2 meters, which equals 196 joules. Remember, work is only done if there is movement in the direction of the force. If you push against a wall that doesn't budge, you might break a sweat, but you're not doing any work in the physics sense. Now let's move on to energy. Energy is the ability to do work. It is the fuel that powers our universe. Energy exists in many forms, including kinetic energy, potential energy, thermal energy, light energy, and more. These forms can be converted from one to another, but energy can never be created or destroyed, only transformed. This is the fundamental principle of conservation of energy.
Kinetic energy is the energy of motion. The faster an object moves, the more kinetic energy it possesses. The formula for kinetic energy is Ke equals 1/2 times mass times velocity squared. A speeding car, a flying bird, and a spinning top all possess kinetic energy.
Potential energy, on the other hand, is stored energy due to an object's position or configuration. A book held above the ground has gravitational potential energy, which is released when it falls. The formula for gravitational potential energy is Pe equals mass times gravity times height above a reference point.
The work-energy theorem, linking work and energy. The work-energy theorem establishes a crucial connection between work and energy. It states that the net work done on an object is equal to the change in its kinetic energy.
In simpler terms, if you do work on an object, you change its kinetic energy. This theorem highlights the fundamental relationship between work and energy, showing that they are two sides of the same coin.
For instance, when you push a shopping cart, the work you do is transformed into the cart's kinetic energy, causing it to accelerate. Similarly, when you lift a weight, the work you do increases its potential energy. The work-energy theorem helps us understand how work done on an object translates into changes in its motion. In simple machines, like levers, the work you apply is converted into energy that makes lifting heavy objects easier. Similarly, pulleys allow you to do the same amount of work with less effort, transforming your input work into useful energy.
In sports, athletes constantly convert work into energy. For example, a high jumper uses work to gain potential energy, which is then converted into kinetic energy as they leap. Cyclists use work to overcome gravitational forces, converting their muscular work into kinetic energy to move uphill. Understanding the work-energy theorem in these contexts helps us appreciate the efficiency and effectiveness of both simple machines and athletic performance.
Power, the rate of doing work. Now let's talk about power. Power is the rate at which work is done or energy is transferred.
In simpler terms, it measures how quickly you can do work. For example, a powerful engine can do a lot of work in a short amount of time.
The formula for power is power equals work divided by time, or power equals force times velocity. The unit of power is the watt, named after the Scottish inventor James Watt, a pioneer in steam engine technology.
Think of two people pushing identical boxes across a room. The person who pushes their box faster is more powerful because they do the same amount of work in less time. Power is a crucial concept in many applications, from rating the output of engines and motors to understanding the energy consumption of electrical appliances.
Conservation of mechanical energy. A fundamental principle. The principle of conservation of mechanical energy states that in a closed system with no dissipative forces like friction, the total mechanical energy of the system remains constant.
This means that energy can be transferred between kinetic and potential forms, but the total amount of mechanical energy always remains the same. This principle is a powerful tool for analyzing the motion of objects in various scenarios, from roller coasters to pendulums.
Imagine a roller coaster car at the top of a hill. At this point, it has maximum potential energy and minimum kinetic energy. As the car races down the hill, its potential energy is converted into kinetic energy, causing it to gain speed. At the bottom of the hill, it has maximum kinetic energy and minimum potential energy. The principle of conservation of mechanical energy tells us that the total mechanical energy of the car remains constant throughout the ride, neglecting energy losses due to friction and air resistance. From collisions to vertical circles. Applying the concepts. The concepts of work, energy, and power are not just theoretical ideas. They have practical applications in understanding a wide range of physical phenomena.
For instance, in collisions, the principles of conservation of momentum and conservation of energy help us analyze the motion of colliding objects. In a perfectly elastic collision, both momentum and kinetic energy are conserved, while in an inelastic collision, only momentum is conserved, and some kinetic energy is lost due to heat, sound, or deformation.
Consider the motion of an object in a vertical circle, like a ball on a string or a roller coaster on a loop-the-loop track. At the top of the circle, the object needs a minimum speed to stay on track, which can be calculated using the concepts of centripetal force and conservation of energy.
In conclusion, work, energy, and power are fundamental concepts in physics that explain how our universe operates. From the motion of objects to the behavior of systems, these concepts are essential for understanding the world around us.